Okay, we're going to continue on here. Last time we got into obviously chapter 4, and in chapter 4, we talked really about geometry. And remember that when we're doing geometry, we talked about really two types of geometry. One is sometimes referred to as the electron pair geometry. That is, again, sort of the geometry of the electron pairs around the central atom in three-dimensional space. And then with that, based on the number of electron pairs that are present and the number of bonds, we also had the molecular geometry, which sometimes people will call the shape of it. When we look at these things and when we're doing geometry, there's really a couple things that we want to do. Whenever there is only a diatomic molecule present, regardless of, like we talked about, whether it is the same elements, different elements, single bond, double bond, triple bond, it doesn't really matter because there's only basically two things there. You can only connect them basically in a straight line, and geometry is always linear. Remember that when we get to three or more atoms, it is always the central atom that you want to look at. And of course, as we also talked about, if you happen to have more than one central atom, then you can look at them each separately, but it should always be the central atom. And really, the best way to do sort of geometry, as we talked about, is look at two things. You want to look at the number of electron pairs there are around the central atom. And again, it doesn't matter, as I mentioned, if it is dots, if they are lines, double bond, single bond, triple bond. It really always all counts as one when you're doing geometry. The other thing that you really want to look at is the number of bonds. And that combination, basically number of electron pairs and number of bonds, will correspond to basically these geometries that we have here. Like if we had 4 electron pairs and 4 bonds, the name of our electron pair geometry would be tetrahedral. And our molecular geometry would also be tetrahedral. If we had, say, 4 electron pairs and only 3 bonds, our electron pair geometry would still be the same. It will still be tetrahedral. But now our molecular shape, our molecular geometry, going to be a little bit different. It's going to be trigonal pyramid. And really, it is, as we talked about, when you draw your Lewis structures and you pretty much have no lone pairs on the central atom, both of the names will be the same. It's only when you introduce lone pairs on the central atom, which in your Lewis structures will be dots, we will actually see different names. And it's really the molecular geometry name that changes. The electron pair geometry name is based on how many electron pairs there are. So that sort of stays the same. But the overall shape of the molecule, as we saw yesterday and talked about, is because we're really, in that case, missing an atom bonded in that spot. It gives the molecule a little bit more flexibility, and it will basically change its overall shape a little bit, and we get these different shapes along with different bond angles. Bond angles, again, are basically related to our electron pair geometry. When we start introducing non-bonding electrons, we do end up getting a little less of a bond angle than we would have if they were all bonded electrons being present. Again, there's a nice table in the notes, also a nice table I made up online on the module section for exam 2 that kind of lists all these things. Probably the best way to do it is just memorization of those two combinations, number of electron pairs and number of bonds. And again, as we also talked about, if you did have, say, multiple central atoms, you basically just kind of treat one at a time and look at what's on the left, and then you would come back, say, and look at what's on the right. So you could do geometry for each central atom separately. Again, just kind of putting your hand over the other part of the molecule. The important part when you do that is, obviously, for example, if this was the geometry we're going to look at, we do want to also include this bond as well, and those electrons when you're counting up the number of electron pairs. Any questions on geometry or any of those things there? All right, you do need to know those, yes, so make sure you do know them. Yeah. All right, we're going to continue on with our bonding journey here. We're going to talk about another sort of idea of bonding, which sort of accounts for sort of the bond angles and stuff that we see. And this is the idea of hybridization. And hybridization basically is the idea of mixing of atomic orbitals. And again, a reminder, our atomic orbitals, our S's, our P's, our D's, and so forth, right, are our atomic orbitals. So a valence bond model describes covalent bonding as this overlapping area. So if we have our couple 1s orbitals here, again, there's going to be this overlapping region in the middle. And that is sort of the region where we would expect sort of the electrons to be shared between the two atoms within that bond. Now, the idea of hybrid orbitals is that when we mix sort of atoms together and they come together, if you think about sort of the theoretical shapes of like the orbitals, you know, you got like an S and you got a P. They definitely are sort of different shapes. They're also different in terms of their energy levels, right? If you think about electron configuration, you know, not everybody's sort of lined up perfectly in terms of energy. Everybody's a little slightly off all those orbitals of where they're located. So the idea of hybridization is that we sort of mix together these type of orbitals. So maybe we take an s orbital and a p orbital, and we mix them together, and we get these hybrid type orbitals. And these hybrid type orbitals, some of the benefits of it is that they result in sort of the same shape. So now when we go to mix, we are mixing sort of orbitals that basically look and have sort of the same shape. Also the same energy. So no longer kind of like we're reaching up in energy or down in energy. So we kind of hybridize these guys, they come together, make these orbitals are all sort of the same energy. It allows for better overlapping with the bonding orbitals and other atoms. And that is sort of the idea of this hybrid orbital. So we take these guys together, kind of mix them, and we end up with these sort of hybrid orbitals, again, sort of all equal in terms of energy. And that's going to allow some nice, better mixing that's going to happen and bonding that's going to happen. Now, the total number of hybrid orbitals that are formed is equal to the number of atomic orbitals that are hybridized. So if you take two atomic orbitals, for example, like our S and our P, that is two atomic orbitals, we would get two hybrid orbitals over here. Yeah, so two hybrid orbitals we form from the mixing of the S and the P orbitals that basically come together. If you mix three of them, you'll get three hybrid orbitals and so forth. So the simplest hybrid orbital you could have is a sp hybridized orbital, and that is much like the name implies. That is taking an S and taking a p orbital. As you can see here in this little demonstration, that is our s orbital, and our p orbital is sort of in this area. And again, they're going to hybridize and sort of make these two sort of kidney-shaped type orbitals that become one here. And we make these hybrid orbitals that basically happen here. And what happens is we will get basically two sp hybridized orbitals is what it's referred to. They're both basically going to be now equal in terms of energy. They will actually end up 180 degrees away. And 180 degrees, if you think about it, that is two letters there. Yes. So two letters is like two electron pairs in terms of electron pair geometry. And that is our linear sort of arrangement that occurs here. So our linear arrangement in terms of electron pair geometry is 180 degrees, and that will correspond there to our sp hybridized orbital. So what happens in this process, for example, if we look at beryllium fluoride, and what we're looking at here is in terms of beryllium, which is number 4 on the periodic table, 1s2, 2s2, right? That's beryllium. These are the two valence electrons for beryllium that's going to be involved in bonding. And that is what we see starting out here in the 2s orbital. What's going to happen, and always happens sort of in the hybridization process, is one of these lower energy electrons gets sort of energized up to a higher energy level, and it gets promoted up there. The result of that is these two orbitals here, an s orbital and one of the p orbitals, will come together and make two hybrid orbitals. We also see that the result of this is, if this is like our px, py, and pz orbital, we end up with two unhybridized p orbitals. So we have two unhybridized p orbitals. We have one hybridized p orbital over here. And this is, again, basically beryllium, where it will be able to bond out with fluorine, for example. Each of these guys has an opening to sort of share an electron, and that is where the bonding would happen in our fluorine with our beryllium in this case. The next sort of type of hybridization is an sp2 hybridized orbitals, and that, much like the sort of name implies, is a combination of an s and two p orbitals basically happening. And because we are mixing together three atomic orbitals, the result of that is we will end up with three hybrid orbitals known as sp2 hybrid orbitals. And again, you can see that here, that is our s, the kind of circle. And again, there is one of the p's there and the second p orbital on the different axis there. And they're going to hybridize once again and create these sort of three hybrid orbitals that are going to happen here. The bond angle, as you can see, there is 120 degrees. And that also should look familiar, right? If you think about the letters we have here, there's S and two P's, S3. So kind of like three electron pairs. Three electron pairs goes with our trigonal planar geometry, right? And that's also 120 degrees here. So that's sort of the electron pair geometry that goes with this is trigonal planar. And that's basically the simplest way to remember it. S and two P's is three, like three electron pairs, just like the previous one was an S and a P, that's two, like two electron pairs. And that's, so how it relates to geometry. So an example of this is boron trifluoride. And once again here, what we're looking at is borons. And that is boron's electron configuration, which is 5, 1s2, 2s2, 2p1. That's the three valence electrons of boron. Once again, this lower electron is going to come up and fill, and then those two p orbitals and one s orbital is going to hybridize. And again, it's going to leave one unhybridized, which is actually the pz orbital in this particular case. This again is going to allow each of these hybrid orbitals to bond out with a fluorine in each of these cases through sharing of electrons between the fluorine and these hybrid orbitals. The next type of hybridization is sp3 hybridization. And again, much like the name implies, we're going to take an S and we're actually going to hybridize, in this case, 3 p orbitals. That's a grand total of 4 orbitals, atomic orbitals coming together. That's going to result in 1, 2, 3, 4 hybrid orbitals, which are known as sp3 hybrid orbitals. And again, in this hybridization, what we're going to end up with is actually 4 hybrid orbitals, as you can kind of see here, 1, 2, 3, and 4. It's going to have a bond angle there of 109.5 degrees. And again, if you count up the letters, an S and 3 P's, that's 4. That's like 4 electron pairs. And that's going to give us our tetrahedral electron pair geometry that goes with that, which is 109.5 degrees difference. And we see this, for example, in methane. And if we look at the carbon here, which is what this electrons are, carbon being 1s2, 2s2, 2p2. This is the 4 valence electrons in carbon. And again, in this case, this lower electron is going to get promoted up, and that's going to allow the hybridization pretty much of everybody here. And that's going to give us 4 equivalent, basically, carbon hybrid orbitals. Each of these can bond with the 1s orbital in hydrogen. Basically, the 1s orbital. And again, we get basically the sort of bond angles that we see in something like CH4, that more tetrahedral arrangement. Everybody pretty much can go through hybridization, except for hydrogen. Since hydrogen only has 1 electron, it does not go through hybridization, but all other elements can sort of go through hybridization. Although we do apply typically hybridization to the central atom, you can also apply hybridization to outside atoms as well. So you can actually do it to any atoms that you want, typically except for hydrogen. Now, when we talk about sigma bonds are bonds where you could kind of think of them as like single bonds. So these are like sigma bonds. And the idea of sigma bonds is the idea of how the orbitals basically overlap with each other. And this is what is referred to as sort of head-on overlap. So they basically just go right into each other straight on. So head-to-head sort of overlap there gives you that overlapping region where electrons are going to be shared between the orbitals. Now, in general, lone pairs as well as bonding uh, electrons can be found in these hybrid orbitals. So although with all the ones we just looked at, essentially they're all bonding electrons, they can make bonds. But hybridization also accounts for the non-bonding electrons that we see in some of these molecules, like say NH3 or water. Um, Hybrid orbitals again results in a more stronger bond uh, than both unhybridized orbitals. So for example, if we look at NH3 and we look at nitrogen, which is number 7 there, 1s2, 2s2, 2p3 in this particular case. Nitrogen basically has 5 valence electrons. So if we look at the nitrogen, what's going to happen in this particular case is we do have our 2s, which has 2 electrons. We have our 2p, which has an electron in each. And if we draw the Lewis structure there for our ammonia, it will look something like this. So how's the easiest way to sort of apply hybridization or do hybridization? Well, the easiest way is we count up basically the electron pairs around the atom that we want to apply hybridization to. In this case, it's going to be the central atom. And we count up electron pairs, and this is sort of important. We count up electron pairs the same way that we do when we do geometry, which means if we do come across a double bond or a triple bond, it will still only count as 1 electron pair when you're doing hybridization, and just like it does when you're doing geometry. So personally, for me, the easiest thing and the easiest way to sort of do hybridization is this. We know when we have an s orbital, there's only 1, right? And we have p orbitals. There are 3 of them. And we actually have d orbitals, which we can't get to, which are 5, right? So frankly, what you would want to do is if you want to assign the hybridization to this nitrogen here, you want to count up the number of electron pairs. So that is 1, 2, 3, and 4 electron pairs. So really all you have to do is start at the bottom here at S and go up and just mark out 1, 2, 3, and 4. So basically what I marked out was an S and 3 p orbitals. So this hybridization is sp3. So that is basically as simple as you can get it to correctly identify the hybridization here. Basically, it's going to be an sp3 orbital. We use 3 p orbitals and we use 1 s orbital, which gives you the sp3 hybridization is going to happen. So that's important because now we know how the nitrogen is going to hybridize in this particular case. So if we go through the hybridization process, what's going to happen is this bottom electron is going to be promoted. And at this point, it does need to go up into like electron configuration. It needs to now come back and pair up here in the p subshell as there's already an electron in there. And when it does that, we're going to end up with an electron there. We're going to end up with paired off electron there. And because it's going to hybridize as sp3, it's going to basically take all these guys and they're going to go through hybridization. And that's basically going to result in, because we took 4 atomic orbitals, we're going to end up with 4 hybrid orbitals, and each of these are going to be sp3 orbitals. And when we look at what happened here, we do have one that's completely filled, but we have these guys, for example. And again, this is all the nitrogen that we're looking at here. So this is the nitrogen atom, basically. And now if we think about sort of our NH3, I'll just redraw it real quick. We can account for basically all the bonds that we see in NH3. I'll just number them. We'll call this 1, 2, and 3, for example. And what would happen is this hybrid orbital here would make a bond with the 1s orbital in a hydrogen. And that would be like our first guy. This guy also has the ability to make a bond with our 1s orbital there and the other hydrogen. That'll be like our second bond. And then this guy as well has the ability to make a bond with our third hydrogen. So that accounts for the bondings that we see in each of those basically nitrogen to hydrogen bonds, a bond between an sp3 hybrid orbital in nitrogen and a 1s orbital basically in hydrogen. These would all be head-to-head sort of overlap, which means all these guys would all be sigma bonds that are happening here. You kind of, again, think of like a sigma bond, like a single bond, basically the first bond that's drawn. And this would be basically a sigma bond, this would be a sigma bond, and this would be a sigma bond. That's going to happen in this case. Now, if we look at it, our drawing, the only thing that's left that's not accounted for at this point is our non-bonding electrons, which are these 2 electrons that are sitting on nitrogen. And that is going to be accounted through this hybrid orbital, which has 2 electrons in it to begin with, which means it has no place to bond. And those are going to account for the 2 non-bonding electrons that we see there in the nitrogen. So this illustrates that the hybrid orbitals can also account for non-bonding electron or lone pairs, in addition to bonding electrons like we see here in the other sort of 3 orbitals. We have bonding electrons and we have non-bonding electrons in this case. Any questions on that there? So if we look at something like water, for example, same idea here. If we draw water, it will end up looking something like this. And if we look at the electron configuration for oxygen, 1s2, 2s2, 2p4, it's got 6 valence electrons that are going to be involved in bonding. Once again, if we want to go through our hybridization for our oxygen in the middle, we're going to count up the electron pairs just like we were doing geometry. 1 electron pair, 2 electron pairs, 3 electron pairs, and 4 electron pairs. All we have to do again is just mark that off. 1 electron pair, 2, 3, and 4. And once again here we see that we have used an S and 3 Ps, which means that the hybridization of this guy is sp3 hybridized in terms of its hybridization. So when we look at the oxygen here and we look at sort of what's happening, we have our 2s that has a couple electrons. We have our 2p that has 4 electrons. Remember, filled upwards first and then downward. The electron down here will get promoted to the next spot there, which is the py orbital. That's going to result in something that looks like this. And still down here, this. It's going to hybridize, as we can see, with all of these guys here. That's going to create 4 hybrid orbitals that are sp3. And again, we can see that 2 of these guys are going to be filled, and these guys will have 1. And once again, this is the oxygen in each of this case, what we're looking at. That's going to allow, for example, our bond here between oxygen and hydrogen to occur. So the 1s and hydrogen will make like that first bond. We also have a spot there that will account for the second bond that we see there, also between the hybrid orbital and the 1s orbital and hydrogen. And again, at this point, we have a pair of unpaired electrons. There's 1, and a pair of unpaired electrons, and there's 2. So all the electrons here in oxygen are going to be accounted for through hybridization. All 3 of these things that we just looked at, which is CH4, NH3, and H2O, they all had 4 electron pairs. And again, they all had an electron pair geometry of tetrahedral. One had all bonding electrons involved in the hybrid orbitals, and the water and the ammonia had a combination of bonding electrons and non-bonding electrons basically involved as well. So hybridization does account for, as you can see, all the bonds that we see, including the non-bonding electrons, and accounts for the geometry that we see in terms of the bond angle. Each of these has somewhere in the neighborhood of 109.5 degrees, as they're all tetrahedral. Water and ammonia a little less than that, but that is sort of the overall sort of angle that we see. Any questions on that there? Now, if we look at something a little bit more complicated in a sense, not really, but we look at something like we drew, I think, yesterday in the study assignment. If we were to draw this, we would end up with something like this. And we need like a double bond action happen there. So we basically have 2 carbons. We have basically, like we talked about, sort of carbon number 1 and carbon number 2. And we could apply hybridization to each of these carbons the same way as we did before. We have our S, we have our P, we have our D. So if we look at carbon number 1 here, we're going to count up electron pairs. And remember that we do want to count them the same way as we do geometry, which means that is an electron pair right there. That is an electron pair right there. And now we would also count, right, since we have 2 central atoms, we would split it there. We would also count this guy right here. And remember that the double bond will also count as only 1 electron pair. So that carbon there has 3 electron pairs, which means if we mark off our little chart here, 1, 2, and 3, in this case, I use an S and only 2 Ps, which means the hybridization of this guy is sp2 hybridized. Any questions on how I got there? We would do the same path here for the guy on the right. It happens in this case, it will end up the same. We have 1 electron pair, 2 electron pairs, and once again, the double bond is going to count as 1, and that also will give us 3, which will give us sp2 hybridization basically occurring in this case. So if we sort of look at what's going to happen in this case, if we look at carbon, which is the central atom on both sides, it is 1s2, 2s2, 2p2, which is our carbon. We are going to get some hybridization occurring here. And we got 2. This guy is going to get promoted up there. And again here, though, we're only going to hybridize an S and 2p. So this is like px, py, and the pz orbital. So we're going to actually only hybridize these 2 guys here. And the result of that is it's going to get us 3 hybrid orbitals that are all same in energy. And this is going to be an sp2 hybrid orbital in each of these cases. But in addition to that, we actually have 1 orbital in this case, which in this case is our pz orbital, that is unhybridized. So we will also have an unhybridized pz orbital. And in this case, they each will have an electron happening. And this would be what is happening here for carbon number 1 on the left-hand side. First off, any questions on that? So we got 3 hybrid orbitals happening, 1 unhybridized p orbital. Because the carbon on the right-hand side is pretty much identical, it's going to hybridize the exact same way. So we will also end up, for our carbon on the right-hand side, 3 hybridized sp2 orbitals, which each end up with an electron in there. And also 1 unhybridized pz orbital in this particular case. And now we have basically the hybridization is going to happen at our central atom. And what I'm going to do now, I think, is erase all my scribble here. Draw the original guy. So now we can think about how all the bonds are going to basically happen in this case. So what I'm going to do is just kind of number the bonds, and I'm just going to kind of show you where everything ends up. So we'll just call this bond number 1. That will be bond number 2. That will be bond number 3. That will be bond number 4. Now we also have a double bond between the 2 carbons. So I'm going to call that bond number 5 and bond number 6. So those are all the different bonds. We obviously have 4 hydrogen atoms, 2 on each of the carbons. Those are unhybridized H hydrogen atoms, which will not go through hybridization. So I'm just going to kind of draw them. They're obviously not correct in terms of energy placement. I'm just drawing them for room placement on the screen. All right, so we got a couple of hydrogen 1s orbitals on that carbon. We got also a couple of 1s orbital hydrogens on the other carbon. And now we could really sort of talk about our bonds. So we'll start with bond number 1. For example, this guy and this guy will come together to make that first sort of carbon-hydrogen bond, basically. We could also use this guy and this guy to come together to make a second hydrogen bond. I guess I should label that too. And that is a bond between an sp2 carbon hybrid orbital and a hydrogen 1s orbital. Now, if we go to bond number 3, we can make a bond between these 2 guys. Again, that would be like our 3rd bond there. And our 4th bond could go here between that. So we've now taken care of pretty much all these sigma bonds. And these are all sigma bonds. These are all going to be head-to-head overlap between those orbitals. So all these guys here are sigma bonds. So what is left? What is left is the double bond between the 2 carbons that are basically happening. And if we just look at the way we draw a double bond, it's basically 2 lines. So it's like 1 bond and then another bond. So bond number 5 here, which is like the first bond of the double bond, is going to actually happen between these 2 guys. These are the 2 carbons, right? So there's going to be a bond here between these 2 guys. There's going to be kind of like the first line in the double bond, and that's going to be a bond between 2 sp2 hybrid orbitals basically coming together and overlapping in a sigma sort of fashion. So they're going to come together and make a sigma bond between them. Now, we need to make bond number 6, which is our second bond there for our double bond or second line. The only thing left to make that last bond for our double bond is what orbitals are left on each carbon that have not been used yet. The only ones that have not been used yet is the unhybridized p orbital, right? So they each have an unhybridized pz orbital. That's the only electron that hasn't been used up yet to make any bonds. And that is actually where the double bond is going to come from. It's going to come from the overlapping of the unhybridized p orbital. Now, because this is an unhybridized p orbital, it is a regular p orbital on each side. So you got this pz orbital and another pz orbital, which is the shape of a normal sort of p orbital. It actually overlaps differently than all the rest of the bonds that we just did. All the rest of the bonds we just did went head to head, straight at each other, and go into overlap. Here, because these are unhybridized p orbitals, we're actually going to get what is referred to as sideways overlap. Above and below sort of the plane of the molecule there, you're going to get some overlapping that's going to happen on that. When you get this sideways overlap, this is the type of bond which is known as a pi bond. So this is a pi bond. And a pi bond will be what's going to happen here. These two guys are going to do sideways overlap and make the pi bond. And that's going to be basically the second line or the second bond in your double bond. And now we've accounted for all the electrons that are going to occur to make these bonds. So a single bond is basically going to be made up of a sigma bond through the overlapping of the orbitals head to head. A double bond is actually made up of a sigma bond and one pi bond, a sigma bond making straight on, and a pi bond with these unhybridized p orbitals doing this sideways overlap. Now, obviously, we know we have a single bond, a double bond. There is also a triple bond situation, right? And in a triple bond, it is a sigma bond followed by 2 pi bonds, basically, to make a triple bond. Any questions on that there? So let's take a look maybe at that. So we take a look at this situation here and we draw the Lewis structure for this guy. We're going to end up with this deal right about there. And again, we have 1 carbon and 2 carbons. We can do our hybridization for each of these carbons. And again, the simplest way is really just to make these things. So if we look at carbon number 1, we have 1 electron pair. And on the other side, that triple bond is going to count as only 1 electron pair. So that is 2. So that is going to mean that this guy is going to be sp hybridized, as we use only an S and a P. Same thing here on the right. This guy has 1 electron pair. And once again, our triple bond is going to be 1, which means in this case, this guy is going to be sp hybridized as well. So once again, we're looking at carbon, which is our 1s2, 2s2, 2p2, which is our 4 valence electrons that are happening there. And again, it's going to hybridize as sp. So it's going to start out like this. We're going to get that promotion of the electron that's going to go upwards. And now we'll put an electron in each of these things. And our 2s. And in this particular case, we're going to hybridize only as sp, which means we're just going to take 2 of those. And that's going to give us basically for the carbon on the left, 2 sp hybridized orbitals. It will also leave us the py and the pz orbital that is unhybridized. So they will have 2 unhybridized 2p orbitals. And again, in terms of the electrons, we will end up with electron, 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 and electron. And this would be what we're seeing for our first carbon there on the left. Our second carbon is hybridized the exact same way. So it will end up the exact same way with two sp hybrid orbitals and two unhybridized p orbitals, or py and pz orbitals, and that should be carbon number 2. So again, if we take a look and try to account for all the bonds that we see in this guy, we'll call that bond number 1. We'll call this bond number 2, bond number 3, bond number 4, and bond number 5 happening there. We will see a hydrogen 1s orbital making a bond right there for number 1. We will also have a hydrogen 1s orbital making a bond right there for our second. Now, what is left is our triple bond between the carbons, basically. And that's 3, 4, and 5. And by the way, again, this is going to be a sigma bond. This will be a sigma bond. The first bond in a triple bond is going to be the sigma bond, and that's going to happen between the hybrid orbitals of carbon. So that will make our sigma bond, which is bond number 3. We now, in this case, have two unhybridized p orbitals in each of the cases. And for our fourth bond, for example, we will have these two guys doing a pi bond. And again, that's going to be our sideways overlap happening here. And then that would leave these two guys here to do another pi bond, which once again is our sideways overlap, to make bond number 5 and 6 in this case. And that will, or sorry, 4 and 5, 4 and 5. There we go. And that will account for all the bonds that are happening to make our triple bond. So again, two pi bonds and a sigma bond will make up that triple bond. The second and third sort of bond in the triple bond is made up of those unhybridized p orbitals sideways overlapping to make that triple bond. I would do my best to draw, but it's probably not going to come out so well, but I'll try. So you got kind of this happening. And again, remember that these unhybridized p orbitals are on different axes. So you got sort of another one sort of coming this way and doing that triple bond sort of overlap between those p orbitals. Any questions on that there? So hybridization also accounts for the sigma bonds, pi bonds, and the double bonds. Triple bonds can be accounted for by using the unhybridized p orbitals. So our unhybridized p orbitals basically are involved in making the double bond second line, and in our triple bond, double bond to second line, and the third line for our triple bond. Any questions on that? Now, there is also our expanded octet. And so far, what we've seen is if we have electron pairs, like our electron pair geometry, we have 2, which is our linear, and that's 2 letters, which is SP. We have 3 electron pairs, which is our trigonal planar, which are 3 letters. We have our 4, which is our tetrahedral. That's an S, a P, and a 3, which is 4 letters. We have 5, yeah, which is our expanded octet. So if we look at 5 is 1, 2, 3, 4, and 5. I've used an S. This is, by the way, our triangular bipyramidal. I've used an S here, 3 P's, and I now got into a D. So that is the sp3 dehybridized, right? Or expanded octet, 5 electron pairs. We also saw 6 electron pairs, which is octahedral. And again, 1, 2, 3, 4, 5, and 6, which will take us to sp3d2. Now, sometimes books will do the D first. They'll do like D2, sp3. I don't know why, but sp3d2 takes us to 6. So this is how hybridization relates to electron pair geometry. And again, probably the easiest way to assign it is just to draw a proper Lewis structure. Make this little box over here. Just check off all the electron pairs you have, and it'll basically give you the hybridization. Hydrogen typically will not go through hybridization because it only has one electron, so that would still just be a 1s orbital and a 1s orbital. Everybody else could go through hybridization. Yeah. Nope. Other questions? So, for example, let's just draw something weird. Let's see. Let's do this. All right. So once you on this one, give the hybridization for all the atoms except hydrogen. And also how many total sigma bonds and pi bonds are there in the entire thing? All right, so take a moment, just assign hybridization for each of these. Assign hybridization, once again, probably the easiest way is just to mark it off. Don't make it more complicated than it has to be. All right, so we'll start with carbon here on the far left. We want to count electron pairs like we're doing geometry. So 1 electron pair, 2 electron pairs, 3 electron pairs, and 4. So that's 1, 2, 3, 4. So that's an S and 3 Ps. So that is sp3 hybridized. Any question on that one there? Now, if we come to the next carbon, it's got 1 electron pair there. And again, this triple bond is going to count as just 1 electron pair. So that's 2. So that's 1 and 2. So that's an S and a P that's basically going to happen in this particular case. And that means that our hybridization there for this particular guy would be SP. Coming to the guy next to it, that triple bond's going to count as 1 electron pair, and we got 1 electron pair there. That's also 2, 1 and 2. So that is going to be sp hybridized in this particular case. Now, if we look at the next carbon in the row there, and we look at what's happening in terms of electron pairs, we got 1 electron pair there, got 2 electron pairs there, and our double bond here is going to count as only 1, so that is 3. 1, 2, and 3. That looks like an S and 2 Ps. So that is sp2 hybridized. Yeah. Any questions on that there? By the way, we could also, if we wanted to, apply hybridization to the oxygen, which you can if you like. So if we did apply hybridization to the oxygen, oxygen has 1 electron pair, 2 electron pairs, and again, the double bond is going to count as 3. So that would be 1, 2, and 3. Actually, our oxygen is sp2 hybridized as well. Yeah. Any questions on that there? How to assign hybridization? Now, in terms of how many sigma bonds and pi bonds are there, if we come back through, just redraw it here so it doesn't get so messy. That triple bond, still, and that. All right, so clearly, right, anything that basically is a single bond is going to be a sigma bond, right? So this is going to be a sigma bond, that will be a sigma bond, that's going to be a sigma bond, that will be a sigma bond. Remember, in our triple bond, it is a sigma bond and 2 pi bonds, which means we do have 1 sigma bond hanging out there in the triple bond part of it. We also have a sigma bond here. We have 1 here. And also in a double bond, it's a sigma bond and a pi bond together, which means one of those guys would account for a sigma bond. So where do we end up with there? 1, 2, 3, 4, 5, 6, 7, 8. We have 8 sigma bonds in this particular case. Now that leaves us pretty much for our pi bonds, which will be found in our double bond. and triple bond. So that's going to be a pi bond, that's going to be a pi bond, and that guy would be a pi bond, which means we will end up with, in this case, 3 pi bonds. Any questions on how to assign hybridization, figure out sigma and pi bonds? That is essentially what you'll need to do. I won't ask you, obviously, to draw out probably the arrows and where all the bonds come together. That was just hopefully to demonstrate what's happening and sort of how everything's coming together. But you do need to be able to obviously draw the Lewis structure, identify the hybridization of the atoms, and what ones are sigma bonds and pi bonds. Any questions on any of that? All right, so we did that guy. So we also, again, just talked about pi bonds, which again is that sideways overlap. Happens with those unhybridized p orbitals, basically making up our double bond. 2 unhybridized p orbitals, basically 4 total unhybridized p orbitals, 2 on each of the atoms, making up our triple bond. Expanded octet, I also got there again with our triangular bipyramidal and our octahedral. We do get into the d orbitals, and that is hybridized as well. Works the same way. Obviously, if we took sp3d, we would end up with 5 hybrid orbitals as we combine 5 atomic orbitals there. And obviously, you would end up with 6 hybrid orbitals in the case of sp3d2. All right, any questions on hybridization? All right, we're going to talk about dipole moments, and we're really going to talk about here polar molecular polarity. So again, molecular polarity basically is talking about the molecule as a whole and whether or not, as a whole, are the electrons going to be shared equally or unequally? Is there going to be a side of the molecule as a whole, not just a bond, but the side of a molecule that's going to be more positive or more negative based on how the electrons are distributed? If the answer is yes, the electrons are basically distributed unequally as a whole, that means that we would have a polar molecule. And polar molecules basically means that there is a side that's more positive and a side that's more negative within that molecule, and it will possess a dipole moment. And a dipole moment is represented with really the same arrow that we use for our bond dipoles. And in the case of a dipole moment sort of arrow, it is pointing to the more negative part of the molecule. And again, this part is really to the more positive part. The more negative part of the molecule obviously would be the area where we have a lot more sort of congregation of electrons kind of hanging out, right? Making it more negative. And obviously the positive side is where those electrons are sort of moving away from as a whole. Now, this should not be confused with sort of bond polarity that we talked about earlier in, I think, chapter 3. And bond polarity, for the most part, uses the difference in electronegativity values, and that was the the 0 to 0.4 is nonpolar, the 0.5 to less than 2 is polar, and so forth. Now, as we did talk about, really, there's only one place where really bond polarity and molecular polarity are basically the same thing, and that is with diatomic molecules. But when we do get into 3 or more atoms, we do have to look at a couple different things. So as I mentioned before, if a molecule is polar, it'll mean overall it has unequal sharing of electrons and will possess a dipole moment. A nonpolar molecule will again pretty much have equal distribution of electrons over the entire molecule, and there really will not be a side that's more positive or more negative. It's kind of like a neutral molecule in a sense, based on how the electrons are shared. So it doesn't get a buildup of charge on one side of the molecule or the other because the electrons are basically spread out pretty evenly over the whole thing. So let's talk a little bit about this. Let's talk about probably the simplest molecular polarity that you could have, and that has to do again with diatomic molecules. And as we talked about, because it is a diatomic molecule, there's frankly only one bond involved. in the entire molecule. So if we had something like hydrogen or even oxygen, this is what sometimes referred to as a homonuclear diatomic molecule. Homonuclear, like homogeneous, same, basically, so same elements involved. If we do the change in electronegativity for either of these, we're going to get basically a zero, which means that each of these have a nonpolar bond. And again, if we look at just something like hydrogen, because this bond is nonpolar, and that is the only bond, then the molecule will also have to be a nonpolar molecule. And that is sort of the beauty of a diatomic molecule, is because it only has one bond in the entire thing. If you can correctly identify what type of bond that is a polar or nonpolar, you will also know the polarity of the molecule as well. So something like these, both of these guys would be nonpolar. If we swap it out for, say, something like HF, as we've seen before, this HF is a polar bond, difference in electronegativity, I don't know, somewhere like 4 minus that, 1.5-ish. And this is going to be a polar bond. And if we drew our little dipole arrow, again, should be heading towards the fluorine. And because this is the only bond in this molecule would also be a polar molecule, where this would then be its dipole moment. Also, again, represented by pretty much the same arrow that's happening. So a heteronuclear diatomic molecule is basically one where there are two different elements involved. And in most cases, that usually will have a dipole moment. What is the case where maybe it wouldn't? Well, maybe you get a diagonal relationship that we talked about in terms of electronegativity, and they actually are zero difference. But in most cases, probably a safe bet if you have a diatomic molecule, there are two different elements involved, probably going to be polar molecule, and it will have a dipole moment. Any questions on those there? Yeah. What's that? Do you need? Yeah, you will not need to draw it on your study assignment, but you do need to identify. So this is basically that last column on the study assignment. And that one you could just basically put polar or non-polar. It would be sufficient. Yeah. You do have to draw the individual bond dipoles that we talked about if it has polar bonds. So if everything was that easy, that would be great, but of course it's not. So let's talk about when we have three or more atoms involved. When you have three or more atoms involved and you're going to look at molecular polarity, you basically have to look at two things. You first have to look at are there polar bonds? So clearly, if you end up with a molecule, in most cases, that do not have polar bonds, in general, that would mean that it's a nonpolar molecule. But if you do come across something that has polar bonds and it's three or more atoms, then you need to move on to the second thing to look at, which is the molecular geometry or the shape. So for example, if we look at our friend CO2, let me draw it. CO2 has polar bonds. We know difference in electronegativity. We also know carbon and oxygen is in the same row on the periodic table. Oxygen is further to the right, which means that there is polar bonds, with the oxygen being more electronegative. So the electrons would be pulling towards the oxygen in this case, and we would draw our bond dipoles like so. So CO2 here has polar bonds. So is this thing going to be polar or non-polar in terms of the molecule? Is this molecule going to be a polar or non-polar? Well, we do have polar bonds. So we do have to look at the next thing, which is the molecular geometry. This has two electron pairs and two bonds, which means the molecular geometry is going to be linear in this case. It's basically a straight line. So if we think about it, we essentially have like an oxygen pulling this way, and we have an oxygen pulling in the other way because it is linear. So essentially, if I took my pen here and I have basically oxygen pulling this way, but I have oxygen also pulling the other way, I am actually pulling really hard. Is my pen going anywhere? My pen is pretty much staying still, right? Because I have basically equal pull this way and this way in a straight line, and they're going to cancel each other out. So although something like CO2 does have polar bonds, because of the geometry, they will actually cancel each other out. And CO2 is actually a non-polar molecule because of that. You could think of it kind of like tug of war, like pulling on a rope. So things are going to pull equal and opposite of each other. They technically will cancel each other out. Also, if things actually head straight at each other or are like pushing at each other, equal and opposite, they will also cancel each other out. So if you have like a swinging door that kind of swings open both ways, you had somebody on both sides pushing equally, right? The door's never going to open, right? It's going to cancel each other out. So something that's kind of pushing in the same direction, equal and opposite of each other, are moving equal and opposite of each other, or, they basically will cancel each other out. So it is possible, and CO2 is a really good example that you can absolutely have polar bonds, but because of the geometry, you could actually will have a non-polar molecule. And that is because these guys right here, these bond dipoles, they are vectors, I believe they call it. And vectors have direction, they have magnitude. And then I fell asleep in physics, but I woke up long enough to remember that again, in certain cases, they do sort of cancel each other out. In other cases, they can actually add to each other, depending on sort of their orientation. So if we look at something like our friend water, and in this case, let me draw it like this, actually. Water also has polar bonds heading towards the oxygen in this case, being more electronegative. The water does have polar bonds. Now, in this particular case, when we look at the geometry of water, it is 4 electron pairs and 2 bonds, which means that is our bent or V-shaped geometry. So essentially what we have in this particular case is we got kind of like this deal, like sort of this guy happening. We have polarity moving towards the top, almost like a string on top, right? And if you think about if you just kind of pulled from the top, the whole thing would kind of move together. And that will create actually a polar or dipole moment actually heading in this direction, where the oxygen is going to be more negative and the hydrogen side of water is actually going to be more positive. And this would be a polar molecule, with the red guy here being the dipole moment. And that is because if you draw the vectors, basically, little head to tail action, they combine this way. Right? That's sort of what's happening in terms of the vectors, in terms of how they come together. As opposed, again, to go in equal and opposite direction, they're essentially subtracting from each other and canceling each other basically out. So when it is 3 or more atoms, those are definitely the two things just look at. Is there polar bonds and the molecular geometry to determine whether or not something is sort of polar or non-polar, the molecule. Now, just like sort of with bond polarity, if something is non-polar, there would be no dipole moment, so you wouldn't draw any type of arrow for it. Who wants to play with vectors? Nobody wants to play with vectors. So a much quicker and easier way to sort of do this, as I apparently wrote over this thing here, is, which we'll do it here, is there are certain geometries which are sometimes referred to as being symmetrical. And we're talking about molecular geometries here. And for you guys, that's gonna be, trying to remember, let's go with trigonal planar. That is tetrahedral. Once again, these are molecular geometries. You got a little bit of triangular, bipyramidal, a little octahedral as some of them. So a majority of all these guys, if you draw the Lewis structure, they pretty much all have no non-bonding electrons or lone pairs or dots on the central atom. And if all the outside atoms are the same, it typically will end up in a result of everybody canceling out and being nonpolar. So for example, if I take this, and frankly, when I look at my Lewis structure, I do not see any dots on the central atom, so no dots. I see all the outside atoms here are the same. They are all polar, by the way, bonds heading towards the fluorines, right? They're all basically heading towards the fluorines, the polar bonds. But they're all going to end up basically equal and opposite of each other in the corners of a tetrahedral, which means it's everybody pulling in equal and opposite sides on the rope. You know, if you had like a 3 or 4 sort of prong rope and everybody just pulls, right? It's just going to kind of sit there in the center. And this is going to be a nonpolar molecule. Now, let's just say, for example, though, I swap out one of the fluorines for a hydrogen. We now have polar bonds, right? Heading this way, heading this way, heading this way. The carbon-hydrogen bond is nonpolar. It has a difference in electronegativity of 0.4, but it still is slightly, you know, kind of going in that direction. So what we have in this case, though, is we have all three of these guys kind of pulling, and this guy here is not really pulling on his side of the rope, right? So he's going to be dragged into the mud in like a tug of war situation, and you could kind of imagine movement happening, and this molecule will now become polar with a dipole moment because of that. So if you have any of these symmetrical geometries where essentially you draw the Lewis structure, no dots on the central atom, everything on the outside is the same, it's going to most likely be a nonpolar molecule. If you draw one of these symmetrical geometries with no dots on the central atom and everything on the outside is not the same element, probably a safe bet is going to become a polar molecule in that case. That's a really sort of quick way that you could kind of look at it. Now, that means that there's also unsymmetrical geometries. And again, these are molecular geometries. So just a few of the unsymmetrical, maybe not all of them. But for your case there, what we got? We have our angular, we have our trigonal pyramid, we have our bent, our V-shaped, we have our square pyramidal, we have like our T-shaped, right? Our seesaw, and so forth. So what all these guys essentially have in common is when you draw your Lewis structure, they will have non-bonding electrons on the central atom, basically dots. And if all the outside atoms are the same, it will most likely be a polar molecule. You'll get some unsymmetrically things happening. So for example, if we looked at our water that we saw earlier, when I look at this, I see dots, see everything on the outside is the same. I know it's polar, basically, molecule. So there are, though, a couple of exceptions to the dots and no dots rule. And the couple of exceptions are the expanded octet linear. And that's the one where basically you have something like that. Something like that, where you got the non-bonding electrons in the linear arrangement. And also the square planar. These two do have dots on the central atom, but they are still symmetrical because basically it's a straight line. So if you have that expanded octet that's linear, the same elements on the opposite sides of each other, they're going to pull equally or push equally, and they will cancel each other out. They'll be nonpolar. And square planar as well. If you have the same elements in that square, they're all going to pull right at 90 degrees equally, and they're going to cancel each other out. So those are two that do have dots, but will be nonpolar if all the elements are the same on the outside. What that essentially will leave you is linear, just regular linear, not expanded linear, just regular linear, which is a straight line. And because it's a straight line, pretty much if they're going equal and opposite, they will cancel each other out. If they're heading right at each other, the bond dipoles, they will cancel each other out. But it is possible in linear that you could have everybody heading in the same direction, and that would then become polar. So it is possible in the linear that you could have polar, but that's pretty easy to figure out because it's a straight line. So this is like a really quick way that you can probably correctly identify, is something going to be polar or non-polar. So if we look at some of the stuff that we drew perhaps before, uh, draw a few of the things that we drew before. So if we just look at these, we could really go through molecular polarity pretty quickly. Here on this one, what I would look at is I see dots. I see everything is the same. That's going to be polar. Here, I do not see dots. Everything on the outside is the same. Going to be nonpolar. Here, I don't see dots. Everything on the outside is the same. Going to be nonpolar. Here, I see dots. Everything on the outside is the same. Going to be polar. And here, these are two things that are the same. Diatomic, that's a nonpolar bond. This is going to be nonpolar. That's basically as quickly as you could do molecular polarity by looking at like dots or no dots. And I would say probably 98, 99% of the time, even higher than that, you'll be correct in just doing it that way. Question on molecular polarity there. Yeah. Okay. Let's take a look at some of these. Again, here's our HCl. That's diatomic. Two different elements going to have a polar bond. Means that the molecule is going to be polar as well. Here's our CO2 that we were talking about. Again, even though it does have polar bonds, that is the linear arrangement, and they're going to basically cancel each other out. Here you can see in the electron density map, you have pretty equal sharing of those electrons, as opposed to here where you have a lot more of the electron density towards the chlorine, creating that negative charge. There's our water, once again, with our polar bonds. Again, unsymmetrical geometry. Everything's the same. Going to be a polar molecule, more negative electrons hanging out towards the oxygen in there. And same thing with our NH3. As the dot's going to be more negative towards the nitrogen, more positive towards the hydrogen. Molecular polarity does affect things like solubility and a lot of the properties that we will talk about. How molecules interact with each other is really affected by molecular polarity. Basically, things will interact well with each other if they're very similar in terms of the polarity. So polar things and polar things work really well together. Non-polar things and non-polar things work really well together. But if you mix polar and non-polar together, you have a problem like we see here. Oil is pretty much non-polar, water is polar. They have no way to interact well with each other, as we'll talk about. They have no way to maintain that interaction because one is basically using a different type of interaction because it's polar versus the one that's non-polar is using a completely different type of interaction with itself. So when they try to cross over, it doesn't mix really well. And same thing here. Soap, by the way, actually has a non-polar part, and this part is polar. And that works well for soap. It's actually this part here is polar, and that's non-polar. And that works well for soap because we usually use soap when it's dirty, right? And dirt is typically non-polar. So this part of soap, which is non-polar, works really well and traps the dirt. That leaves the polar part of soap on the outside, and that's really good because typically after you use soap, you use water, which is polar. So this water will then be attracted to the polar side of soap that has the dirt trapped inside, and it will wash out the soap that takes the dirt with it on the outside. So if we look at these things here, we want to know, are these guys going to be polar or non-polar? So take a second to decide polar or non-polar molecules. Okay, so let's take a look. Really, you can do it one of two ways. If you have electronegativity values, you can just make sure there's polar bonds. Between nitrogen and oxygen, there is a polar bond heading towards the oxygen. This is actually non-polar between nitrogen and chlorine, right? Difference in electronegativity is 0. But really, you can just look at it and go, I see dots. They have different things on the outside. So this is going to be angular type of deal. And basically, if you think about it, you basically just have that one side where you're just going to pull down on it, and you can kind of imagine the whole thing moving. And this would be a polar molecule. Here you have basically no dots on central atom. Everybody on the outside is the same. That's going to be non-polar molecule. And again, we do have polar bonds here between the sulfur and the oxygen, with the oxygen being more electronegative. So we would have polar bonds, but this is going to create a triangle, right? Trigonal planar, where basically everybody is pulling equal and opposite of each other, like on a string. And basically nobody's going anywhere. They're going to all cancel each other out. And this would be a non-polar molecule. Any questions on those two there? Yeah.
Because I see S and O, there's a double bond.
It will have no effect on polarity, molecular polarity, if it's single, double, or triple. Yeah, so really for that unsymmetrical, you want to look at the dots or no dots and what's attached on the outside. And again, this is another example where you can have obviously polar bonds, but because of the geometry, they're going to cancel each other out in the case on the right. Other questions? And that one's we did, and that should wrap chapter 4, I think. It is. All right, any questions on molecular polarity?